The last thing I want to tie in with limits is how it's related to the derivative. So we have this theorem, theorem 2, and it connects directly the derivative with the limit of the difference quotient. So the slope at f at a is given by the limit f prime of a is equal to limit as delta x approaches 0 of f of a plus delta x minus f of a over delta x. Well, why should that be the case? I'll do a rough sketch here because this limit, if we look at, we let delta x be infinitely close to 0, but delta x not 0. So this means that not 0. This means delta x is an infinitesimal other than 0. And then the limit as delta x approaches 0 of f of a plus delta x minus f of a, all divided by delta x, is the standard part of f of a plus delta x minus f of a, all divided by delta x. But you should recognize that by now as exactly the slope of our function, provided it exists. So this equals f prime of a. So, and in any other standard calculus course, this is the definition you would have been given as the derivative, is the limit of this object. So that's, if you remember in part 1 of these video series, I said that you would have been introduced to limits at the very beginning of the course, and that's because you need limits to define the derivative. Well, we defined it using standard parts, and we see that standard parts and limits are really just two sides of the same coin. So let's just for smiles, I mean, we know how to compute derivatives using the standard part, but let's compute a derivative using this limit definition. So say I want to know what is the, if f of x is equal to x cubed, let's use the definition, use the limit definition to calculate f prime of, I don't know, say 2. So the limit definition, f prime of 2 is the limit as delta x approaches 0 of f of 2 plus delta x minus f of 2, all divided by delta x, which is equal to the limit as of delta x approaching 0. So this is 2 plus delta x cubed minus 2 cubed all over delta x, which is equal to the limit delta x approaching 0. So cubing this out, I'm going to use my my little tree. So 1, 1, 1. So this is for squares. These are my coefficients for cubes. So I know it's going to be 1, 3, 3, 1. So this will be 2 cubed. So that's 8. Plus 2 squared 4 times 3, which is 12 delta x, plus 2 times 3, that's 6 delta x squared, plus delta x cubed minus 8, still all divided by delta x. Now the 8 and the 8 cancel from addition and subtraction, and now every single one of my terms have a delta x, so I get some canceling there. So this delta x cancels with that one. The degree goes down by 1, and this goes down by 1. This becomes a 2. So this is equal to the limit as delta x approaches 0. What's left over? 12 plus 6 delta x plus delta x squared. And we know that delta x is going to 0. So this whole term is going to 0. This whole term is going to 0. And so the entire expression is going to be 12 plus 0 plus 0, which is 12. Boom, that's the derivative at 2. We could always double check to make sure that we're not crazy since we've got rules. We know that f prime of x is equal to 3x squared. And so f prime of 2 is equal to 3 times 2 squared, which sure enough is 12. Good thing we didn't do any mistakes here, but so that's how we would use the limit definition of the derivative to compute the derivative. It's just good to know, and it's good practice. You'll have practice plenty in the homework doing stuff like this. And again, this is the standard definition in any other calculus course for the derivative. All right, that ends our section on limits. Good luck with your practice and have fun.